you. Just remember, when you want to do your hair good, just hair through like that and let it do its own thing. Hair is a living thing, even though it doesn't hurt you when it gets cut. Okay, it hurts a little bit because sometimes the style can be kind of shit. But this is the big one. This is my big invention. Well, they're all big inventions, but this one is quite a lengthy one. So this blog video is going to have a lot of content. It's probably going to be one of my longest ones. I have to have a script over here just to make sure I'm keeping track with what I'm saying and I'm getting everything in there. I'll probably have to add addendums later to or in descriptions just to make sure I get everything in it. It's a simple concept with that's really big. So let's start off with some simple things. Chemists, because chemical reactions used to react in certain proportions of weight. Now I know they'll say, oh, certain proportions of particles, but we'll get to that later. They used to react in certain proportions of weight, and you couldn't react below that proportion of weight or above that proportion of weight. And that's where the particulate nature of matter came from. That idea that you're sticking together little balls of things, so you can only have certain amounts of certain things. And that's where particulate theory came from. Now, unfortunately, that doesn't actually apply to everything that matter it does. If you look at a solution can be a change its chemistry. It can be a chemical with an infinite spectrum of weights between the two materials. So the two materials mix, and up to a certain amount of overlap, they'll actually be different chemicals depending on their concentration. And you see it with acids and bases, and you see it with alloys and metals. You can get across the spectrum, you can get different properties, and certain properties appear and certain properties disappear. So it's not true that all chemical reactions only react in certain proportions. So that's the first part of chemical continuum theory. So what that leads to is, you see, Leibniz, the inventor of calculus, when he was first working on calculus, he was like dividing things down and down and down, and he did it an infinite amount of time. And that's what chemical continuum theory is that the idea is that the properties of the chemical don't go away or don't become from the shape of the chemical or the shape of a pattern inside the chemical. The chemical properties are the same all the way down, and that's what chemical continuum theory is. So I'll do a basic. Now, forgive me because this is a layman's description. I do know about the whole concept of wavelengths and light, but I'm going to use the color red, and what I'm going to do is just fill in a block of red. It's probably not going to be very full because the marker isn't very wide, but I'll give you, it'll just imagine it's a single color. I just keep coloring and coloring until I get it right. Wish I had a better big red pen on this. Anyway, so you have the block of red like that, right? Now if I do this, it's still red there, and it's still red there on the same side. Now, the idea of chemical continuum theory is I can do that again and again and again, and there's no point at which what red is becomes something else. And that's the kind of crux of chemical continuum theory. Now, if I took a big block of iron or a big block of, see, I like natural things and I like using natural things in my explanation. So I took a big block of cellulose, our big block of, we'll do cellulose in green. I think I have a green over here, so I'll do a little block of cellulose, and I'll do iron in blue. So that's cellulose, and let's go for our metal, which is blue, which is, do I have a blue marker? I have a blue pen. I can I'll do a small blue pen. What I'll do is I'll just streak it, so it's kind of, it'll be blue and white, but just imagine it's just blue, the block. So again, imagine this is cellulose made from wood. And if I chop it in half, it's still cellulose on that side and cellulose on that side. And I can do that an infinite amount of times, an infinite squared amount of times, and the chemicals come from their properties, not from their physical shapes and sizes. I do the same with this one, iron. That's the exact same thing. Now, iron is actually grainy if it has a bit of carbon in it. So there are. It's not an exception to the rule, but it's like if you make a fruit cake, you have that material that you have like spots of red and spots of white, but just three-dimensionally. So that's the chemical continuum theory of matter. Now, just give me a second. I'm just going to go over my notes, and I'll be back to you in a sec. So can I pause the stream? I'm kind of new to the streaming thing, so I'll just quickly go over it. You can skip ahead. I'll give you a thumbs up when my next talking bit is coming up. Okay, so subtheory. Okay, so subtheory is how do gases, liquids, and solids work in this scenario. So I'm not sure if I'm going to be able to draw this on paper. So there's three types. There's more technically, but for now we'll deal with the main three. There's three types of forces between matter, and that is that. Just sorry, I've taken my time. And let's give it a nice pink, shall we? Okay, so these are the three different types of forces in matter. So that is tensile force. So the two at the top, the red two, are being pulled together by the arrows. I'll discuss a concept they call conductive field theory, so that each bit of matter has a field that can conduct into certain things. So conductive field theory is kind of how it works. But for now, we'll just go with the forces. The two forces pull together the matter. The second one is compressive. So compressive forces push matter apart. So if you have compression inside your material, it's pushing the matter apart. And the third one is shear. So if you want to move by something, so it's kind of hard to see in the pink there. So if you want to move by something, say if the one on the left wants to move down and the one on the right wants to move up, that's shear force. So what shear force is it's a form of force that tries to either push things in the opposite direction or pull things in by each other. It's usually a frictional force or a kind of a tensile force that kind of connects. So a connected field is another thing I'll also be going into conductive fields and connected fields. But those are the three types of forces. Now for a liquid, what happens in a liquid is that, we'll start in the middle, a liquid. So a liquid has a balance between compressive and tensile forces, an equal balance, but it has very, very little shear force. So that allows it to shape, to deform quite easily. And that's what makes a liquid. A solid has a compressive and a tensile force balanced where it is in its shape, but it also has shear force, which makes it retain its shape and not become a liquid and be able to flow by itself. And then the last one is a gas. A gas gets expanded. Now heat is another what I call a conductive field. So we'll be going into that later, what heat is. I'll actually make a note of that. Just take a quick little note over there. Heat. conductive field, and tensile and connected field. So I'll go over them later as well if I don't have them in my notes. Heat, conductive field. So what heat does is it pushes matter apart, and eventually the tensile strength gets so weak that it can't compete with the heat. So its tensile strength is completely gone, and all that's left is its compression strength. So that allows it to expand to fill any chamber. So that's kind of the basics of the solid, liquids, and gases in it. I'm going to do another note check. I didn't do the thumbs up last time. I'm sorry. So if you want to, I apologize. You're going to have to just listen along. You're going to have to just listen along because I'll probably forget on the next one. Oh yeah, I should also mention density. So density is the amount of volume per volume, or volume of matter per space. And so as you compress the material together, its density goes up, and if you let it expand, its density goes down, and that contributes to the strength of the fields that the materials are experiencing. Okay, Brownian motion. Brownian motion should work in solids as well as liquids, but only works in liquids. This should suggest that Brownian motion is caused by little flow fields through the material, like jittering it, and the hotter you make it, the faster those little fields flow around it. So I know Brownian motion was kind of one of those proofs of the heat. Heat is motion theory. That's another thing I'm going to have it down. Heat is not motion in this theory. Heat is a conductive field. It's kind of like a liquid that can go through matter. So heat is a conductive field. Okay. Okay, so there's another part of this. Electrons are infinitely divisible. You can cut electrons in half and half and half and half and half. So electric charge is infinitely divisible. There's no such thing as electrons. When you have those little sput images that they give off in their quantum mechanical testing, what's happening is that the conductor is building up to a point till a burst of electrons can actually pass into space. It's not a continuous stream with just dots. It's what happens is the electric charge is building up in the cathode ray gun till it goes sput, till it gives off a sput. So it's kind of like building up like a balloon and then popping, and building up like a balloon and popping. So it's like sput, 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 kind of like a whoopee cushion, basically. Okay, so another proof for this theory is the electrical breakdown of space. You can get, even though there's like supposed to be only one particle in a trillionth of the space inside a vacuum, if you keep pumping, you can get the breakdown strength of a vacuum much lower, even though it should be leveling off. So that's another proof for this theory. So here's the next part of the theory. This is a big part of the theory that's very, very important. And it's called the ghost in the wall theory. Ghost in the wall theory is basically this idea. We treat mass like it's digital. Two things come together, they impact, and then they can't, once they impact, it's like they're instantly solid. There's like the two materials can't occupy the same space. They're just instantly solid against each other, creating like an infinite acceleration just at the very ridge. But ghost in the wall theory is like what it says. If you take that chemical continuum theory, imagine there was no space in the wall, and there's no space in the ghost, and the ghost was sitting in the wall. They'd be overlapping in the same positions in space. So that's ghost in the wall theory. It's it's a cool nickname, chemical continuum theory. My sister used to call smudgy theory, which I quite appreciated. But the maybe you could do the smudgy theory where the things that are sub-zero are kind of smudging into the things that are non-sub-zero or something like that. So smudgy theory is a great theory for that. But that's ghost in the wall theory. So matter can overlap in space. You can see a prime example of that if you take alcohol, pure alcohol and pure water, and you mix them, and their volumes are not equal to the sum of their original volumes. So they're actually overlapping in space. So that's ghost in the wall theory. I'll just do a quick. Oh yeah, the first kind of instance I solved that. I didn't come up with the theories right then, but was in Command and Conquer, the computer game Tiberian Sun. And there's this glitch where all the units went out of their APC, but they were all standing on the same spot. So when I clicked on one and moved it, there was still a guy there. And I had to click on them to get them all to spread out from being overlapped on the same spot. So that's basically the crux of the theory, is that matter can overlap on the same spot. Now, when you compress matter, part of that compression might be that the matter's overlapping. Part of it might be that it's shrinking, its volume is shrinking. So there's kind of two things that might be with that. So that's ghost in the wall theory, or matter overlap theory. What else we got? Oh yeah, the description. So like marbles were like infinitely strong marbles hitting off each other is kind of like the way we used to see matter, rather than being able to sort of like just ever so often just overlap in the same position. Of course, as the overlap goes up, it will get denser and denser and push itself out. Okay, let me see how it works. Wall matter overlap subtheories. Okay, we're getting good. We're getting good. Oh yeah, the matter overlap theory also works for electric charge. So it would explain why coppers are conductors, is that the electric charge is able to overlap the conductor rather than just being fitting in lots of little spaces in between. It's sharing the same space on the same spot. And this also leads to my other three types of forces. So with the conduction forces, there's three types of forces, and I'll draw them out. So I'll draw them in red and blue. Okay, so there's three more forces with the conduction stuff, or the ghost matter. The ghost matter theory is what it's about. That was another name for it, ghost matter theory. So that up there is called conduction, and you can make those really, really long, and they move through each other from a force. So the blue will move to the left and the red will move to the right. This one is called attraction. So they'll attract overlap. So they'll pull each other into each other. So the blue will be pulled into the red and overlap with it. And then the last one is the opposite of that, is they'll be pushed apart from each other. So the red will be pushed out of the blue. You can kind of see that when certain materials are molten and they're soluble in each other. And then when they cool down, they kind of get pushed out of each other. Okay, so that's the thing. Additional space is matter, transparent, superconductor, solid. Okay, so that was a theory I had, which was that space is a matter as well, but it's a superconductor to our mass, and it can be a solid, liquid, or in gas. Another one was space can conduct through itself, or you could have multiple spaces conducting through each other. Electrical charge overlap. Matter doesn't conduct well through space. So electrical charge doesn't really conduct well through space. Maybe it is space. That's another theory. And that's why you build up the sort of voltage spikes to have the electrons moving through it. In here, there's a lightsaber invention. So if you had a positron and an electron, and they spun around each other, and you sent it out of the sword and let them sort of collapse in towards the center, that would make a lightsaber. So that was my invention of a lightsaber. Okay, so the next big part of this, and it's already dealt with. Mathematicians deal with heat this way. They don't deal with heat as motion. They deal with heat as a flowing liquid or a conductive liquid or a conductive field. You'll find that most effective mathematics, when dealing with heat, treat it as a conductive field. So what a conductive field is, it's like a liquid or maybe even a gas that can flow into things. And when it flows into matter, it forces it to expand, and then it can flow out again. So it's like it can conduct in and out of matter. That's one of my theories, was that that charge, negative and positive charge, or heat, are heat charged negative or heat charged positive, and that's what electrons were. So that's one of the theories. So the conductive theory of heat was that, and that's also why light waves are that shape. And heat, when it travels into space, it might be space, is one theory, or another theory is if it travels into space, it causes it to ripple, and that's what light waves are from hot objects. Heat being space might be a good theory, because things getting hotter might pull the matter apart, and that's what the heat might be doing, is it might be forcing the matter apart. The space might be forcing the matter apart. It might be a good way to get higher vacuums, is to heat the vacuums. See, particle accelerators don't accelerate particles. They accelerate bunched gas whiskers. So whiskers of gas, because when the things are traveling very fast, it's like a whisker, because if you shoot two electron beams in the same line, they'll start to attract to each other. So you're shooting these whiskers of very, very thin whiskers of material, and then they're hitting at the point of the particle accelerator. So chemical reactions. How do chemical reactions, the ones that the original chemists work at, and why do they always form set ratios? My theory behind this was that when the chemicals overlap to react, but they also give up or gain energy to a certain point, and that's why they become definite ratios. They give off their energy, and then hit equilibrium. And then if you were to force them further, they'd be taking on energy, and that's why chemicals mix in certain ratios. Let me see. Another thing was the idea is that when you mix chemicals or break them apart, you might be able to create new properties in that matter that didn't exist in the other ones. That falls into one of my theories I called it's all elements theory. So when you split apart water, you're not breaking it down into into parts of water. You're breaking it down into two new elements by splitting. And then when you're bringing it together, you're creating an element by combining. So all chemicals are technically elements. And that's one of the theories I was playing with. Another interesting one with that is with phosphorus. If you heat phosphorus to a certain temperature, it chemically changes. Even though it's meant to be made of particles, its properties actually chemically change. It's like it takes on the energy and then binds the energy into itself. Another one was the periodic chemical table. The periodical chemical table is it's our limits. Just because we can't break something further into further elements doesn't mean that it is an element. And I think that was one of the problems with the way we treated the periodical table. We kind of gave up once we tried our best at breaking down the elements. There was an experiment I was wanting to do called breakdown electrolysis. I wanted to get liquid nitrogen and pass enough voltage through it that I could electrolysis the nitrogen and turn it into a new compound by breaking it into two different, a positive and negative charge based nitrogen, doing the same with oxygen for sort of like super oxidizer fuels and things like that. Energy may become the new properties is another idea. There's another one called air alloy. So instead of treating the air like it's made up of this percent oxygen, this percent nitrogen, treat it like it's a gas alloy. So the air is actually a gas alloy, and you can split it into those things, but it is actually an element in itself, a gas alloy element. Oh yeah, I must make mention of Avogadro's constant. I don't like that, just because if that's out by even a millionth of a millionth, it's wrong. So it's I just don't like it. Take that whatever way you want. Let me read through that. Oh yeah, there's another idea I had, which was you split water in two and it becomes hydrogen and oxygen, but we've never tried to split it into another way. So there may be other elements we can create from water just by splitting it in two in different ways. And maybe we can use other chemicals as the splitting agents. And maybe you can connect them to electricity as well. Chemical summoning theory. The first time I came across this was in this cartoon where to color your man's outfit, what they used to do is they just put a pattern on the background and then they cut out his outfit and moved the cut to different places along the element. And I always thought that was like summoning in the chemical in different places to actually be the chemical. So some of the chemicals, all kind of, maybe all, but some of the chemicals exist in the background, and you're kind of pulling in certain chemicals and you're pushing out certain chemicals to get those chemicals in. Endless chemical element theory. So this is kind of the idea of you can keep on splitting forever. So you can split water into hydrogen and oxygen. You can use breakdown electrolysis, split them into two new compounds, and you keep on splitting forever and ever. And chemical continuum theory allows you to do that because it's not based on the size. It's just based on the difference in chemical properties. So you can create an infinite amount of elements and an infinite amount of compound elements. And that's kind of like the theory of how it works. Or there's another one called scalar properties. So properties that can be scaled, strengthened up and down. And you can split an element by splitting its scalar into two smaller scalars. And that might be just two smaller scalars, or it might be new properties. Another thing is you can split properties is another idea, so that you can split properties into new properties, or you can split properties into scalars. So the other thing is there's a few other fun ideas you can play with, which was inverse plastics. So plastic that you put a chemical into it and it depolymerizes. So when you're 3D printing, if you want to represent the gas parts of 3D printing, you can put that polymer in place and you can just put the chemical on it and it'll turn it to gas slowly. So you can literally make a car out of complete solids. There's a thing called laminate manufacturing, and that's the fastest 3D printing method. If you combined it with that, you could probably 3D print most things very, very quickly. So I think that's pretty much everything. Yeah, that's everything to do with chemical continuum theory and how I think matter works. You could throw in things like protons and neutrons conceptually. I don't believe they're there, but you can throw them in conceptually by having concepts of like things that can only be a certain size. They could act as sort of compasses in size throughout space, or you could have things that can only get to a certain bigness and can't get any bigger, or things that can only get to a certain smallness and can't get any smaller. And those things then would act like your quantum properties and things like that. The other thing is that we treat time as a now, but the now might be bigger than we think. And that might be another reason why quantum properties work if they were taken on. I don't believe in quantum physics, but I believe you can create quantum physics through chemical continuum theory. So that's my theory. It took half an hour to explain. I hope you enjoyed the show. On with the show, this is it. In no lives will bring. On with the show, this is it. Wow, it didn't work. Give it time, give it time. Just watch. It'll do its magic. See? Magic. Hair is magic. Remember that. Your hair is magic. Okay, so we'll end stream there. I hope this was informative. This is the way I was in chemistry class one time, and I remember hearing about the octet rule, and I was like, "What is this? What the hell is going on? This is really weird. This isn't how matter works." So I came up with this theory, and so far it seems to be working. So maybe it'll be disproven. I hope not, because I think it's a very beautiful theory, and I hope it's the way matter works. So thanks for watching, and I'm not going to say throw up a like or subscribe. I'm going to say you do you, bub, and sometime maybe I'll get to talk to you and we'll have a nice conversation. So ending the stream now. Goodbye.